So now we will see another part which is called as a pulse shaping. It is an important part in communication engineering. So let us see this equation. This equation is basically the power spectral density of a pulse, of a train of the pulse, where PF is a Fourier transform of that pulse, as we have seen in the previous lectures. R0 and Rn are basically this statistics defined in previous lecture. TB is the duration of the pulse. Now question arises, if I am interested in controlling the PSD, because PSD has to be favorable, as far as I need to control something which is called as the intersymbol interference, then what should be done? How to control that? So to control the PSD, I have two options. One is I should work on this part of the equation so that the power spectral density is controlled. I can get favorable PSD. And I have second option, which is I must work on the pulse PF. So now we will see how to work on the pulse PF so that we have favorable PSD and we can control something which is called as intersymbol interference. So we'll try to understand what is intersymbol interference and how to have a proper shape of the pulse so that this intersymbol interference could be avoided. So let us consider transmission of the pulse PT. Here pulse is of the height 1, the level of the pulse is 1 volt, its duration is TB, and this is passed through a channel whose transfer function is given by this expression, this particular figure, that is, it is constant for minus omega c to plus omega c. So omega c is bandwidth, and the output of the channel would definitely be multiplication of the transfer function of the pulse and the Fourier transform of the pulse, that is PT. Either I should convolve PT with the impulse response of the channel to get the output, or I should multiply the transfer function of the channel with the Fourier transform of the pulse to find the output. Now what is the Fourier transform of this pulse? The Fourier transform of this pulse is a sinc function. So this is a rect pulse of the width TB with the Fourier transform TB sin C pi f TB, which is drawn here. So the zero crossings are coming at 1 by TB, 2 by TB, and so on, minus 1 by TB, minus 2 by TB, and so on. Now when the output is multiplication of HF and PF, that is a multiplication of, output is multiplication of this and this, these two are multiplied. So when this function is multiplied with this response, so this is what we are going to get the output. In other words, whenever a band limited signal, what is this? This is a band limited signal. What is this? This is a band limited channel. And what is this? This is a band unlimited signal. So whenever a band unlimited signal, or either I should say band unlimited or frequency unlimited, is passed through a band limited channel, then the output is going to be, at the output I am going to get a band limited signal. In other words, this band unlimited signal is converted into a band limited signal when it is passed through a band limited channel. So how this will affect? So as we can see, there is a rule in communication. Whenever there is a compression in time domain, there is going to be expansion in frequency domain, and when there is an expansion in frequency domain, there is going to be compression in time domain. In this case, as can be seen from the output, this pulse is compressed in frequency domain. This pulse, which was band unlimited, is compressed in frequency domain. That is it has become band limited. That is why when we take its inverse Fourier to get the output pulse, that is P naught T, because this is in frequency domain, we will take its inverse Fourier transform to get P naught T or Y naught F, whatever we call. Then this compression that is becoming band unlimited to band limited causes pulse expansion. Pulse expansion as is shown here. In other words, the pulse which was supposed to be of this duration will expand. So this was the duration for which pulse was supposed to be there. However, this pulse is expanded in this duration, which is supposed to be the duration for some other pulse. This causes expansion. That is there is expansion in the pulse, and expansion causes something which is called as ISI. I'll repeat again. What is happening is when I'm passing a time limited pulse, which is actually a band limited. Time limited is band unlimited. When I'm passing a time limited pulse, that is a band unlimited pulse, through a channel which is band limited, because channel will always be band limited, then at the output I'm getting a band limited signal. Since this band unlimited pulse is converted into a band limited signal, that is why it causes expansion in the pulse. Expansion means the pulse which was supposed to be for this duration will now expand after this duration and interfere with some other pulse in this region, because this portion is basically for some other pulse. That is why this phenomena is called as ISI, or inter-symbol interference. So question arises, what is the reason of ISI? So reason of ISI is, the main reason of ISI is because our channel is band limited and signal is band unlimited. So the second question arises, how to avoid this ISI? So prima facie, the problem is occurring because signal is band unlimited and channel is band limited. Now question arises, can I make this channel as band unlimited? This is not possible, because it is not possible to have band unlimited channel. Channel is always band limited. So what can be the other solution that we have to explore so that this problem can be avoided? Why we want to remove this problem? Because this one pulse when interfering with the other pulse is not good thing, because it will cause an error in the reception of the second pulse, and amount of the interference will increase the amount of error, that is bit error rate will increase when ISI is more. Now we will see how to avoid this ISI. Before entering into solution, we can see ISI from different perspectives, and the perspective is this. As can be seen, this is a rectangular pulse. This is a channel. This channel is a low pass filter. This is equivalent to low pass filter. That is why it is as good as we are passing a rect pulse through a low pass filter. So when this pulse is passed through a low pass filter, the output will be like this. So that is, in this, initially it will charge, my capacitor will charge with the time constant RC. The charging time constant is RC. So once it is charged, then after it will discharge through, it will remain charged for the duration, that is this, and after that it will start discharging through a lot, that is RL. So the discharging time constant is RL into C. So for a given C, depending upon the value of RL, we will get this curve. So this curve, this particular shape will be defined by, for a given C, it will be defined by the value of RL, and this is interference. It is the same effect that we have seen just now, that is through this explanation. So it is the same phenomena. Same phenomena can be understood with either this method or using this way. Now we will see how to avoid ISI.